This presentation is an addendum to the presentation on Iran's path to a plutonium weapon. After further research, I realized that the question is not as simple as extracting plutonium from spent fuel rods from a reactor. Here, I will try to explain other critical factors. These factors center on the amount of plutonium-240 in the spent fuel rods. Plutonium-239, a fissile isotope of plutonium, is used for the core of implosion nuclear weapons, similar to that of Fat Man that was dropped on Nagasaki, Japan on 9 August 1945. It is not a naturally occurring element. It is produced in nuclear reactors via neutron capture by uranium-238, the most prevalent isotope of uranium. After 2 radioactive decays by beta emission, plutonium-239 is produced. This was first done at the Hanford, Washington reactors built for the Manhattan Project. That plutonium was used in the Trinity test device and Fat Man. When U-238 absorbs a neutron in the reactor, it becomes U-239, which is unstable. It decays by beta emission with a half-life of 23 minutes to form Neptunium-239, which is also unstable. Neptunium-239 then decays by beta emission with a half-life of 2.4 days to form plutonium-239, the fissile material for implosion weapons. Unfortunately, this is not the end of the nuclear processes in the reactor. The free neutrons from the fissioning of the U-235 fuel are also captured by the newly created plutonium-239 to form plutonium-240. This isotope is not useful for nuclear weapons because it is unstable. It decays by both alpha decay and spontaneous fission. Although alpha decay is the predominant process by far, the spontaneous fission is the serious problem for plutonium weapons. Plutonium-240 undergoes spontaneous fission at a rate of 475 fissions per second per gram. These spontaneous fissions produce an average of 2.2 neutrons per fission. In a weapon core, these extra neutrons greatly increase the chance of premature fission of the core material, that is to say, plutonium-239. This leads to a finite probability of a pre-detonation and a fizzle of greatly reduced yield. This is the reason plutonium weapons require implosion to assemble the supercritical core significantly faster than that required for uranium weapons. The probability of pre-detonation depends upon the percentage of plutonium-240 in the plutonium core. The longer the plutonium remains in the reactor, the more plutonium-239 is converted to plutonium-240. As this contamination increases, the plutonium becomes less useful for a weapon. This figure shows the probability of pre-detonation for 4 different percentages of plutonium-240 in a core similar to the Trinity device and Fat Man. These are referred to as grades of plutonium. The 2% curve corresponds to weapons-grade plutonium. This was the grade for the Trinity device and Fat Man. The U-238 to plutonium-239 rods were left in the Hanford reactors for only 90 days to minimize the contamination of plutonium-240. The 5% curve is the upper limit for weapons-grade plutonium. The 19% curve is referred to as fuel grade, and the 25% curve is considered reactor grade. Reactor grade is the typical grade of the spent fuel rods from civilian power reactors. The implosion assembly time is about 1 to 4 microseconds. During the Manhattan Project, a pre-detonation probability of 20% was considered acceptable. It is obvious the 2% curve is within this limit to almost 4 microseconds. The 5% curve, the upper limit for weapons grade, is within this limit to about 1.5 microseconds. However, the other two curves have unacceptable probabilities of pre-detonation even before a 1 microsecond assembly time. They are not considered useful for an implosion weapon unless a significantly lower yield, that is to say, fizzle, is desired. This last curve shows the pre-detonation yield versus pre-detonation time, again for a Fat Man type core and implosion assembly time. If pre-detonation occurs almost immediately, the minimum fizzle yield is 2.04 kilotons. If pre-detonation holds off for 3.6 microseconds, the full yield of 21 kilotons is achieved. That is the reason the grade of 2% plutonium-240 gives the greatest probability of achieving the full yield. If lower yields are acceptable, then higher concentrations of plutonium-240 can be used in the core. Because the fuel rods in a civilian power reactor remain in the reactor for extended periods of time, plutonium-240 builds up to levels unacceptable for nuclear weapons of significant strategic yield. The reactor must be specifically operated to produce weapons-grade plutonium. The plutonium must be removed before the plutonium-240 increases to a grade that would only be useful for weapons of significantly lower yield. In addition to the pre-detonation issue, there is a health hazard associated with high concentrations of plutonium-240. The spontaneous fissions release neutrons and gamma rays. The alpha decay presents a radioactive issue in the handling and processing. Although alpha particles are easily stopped by even a sheet of paper, inhalation of plutonium-240 leads to inner organ damage from the alpha particles. Lung cancer is especially problematic. The fission products from the spontaneous fission of plutonium-240 are also radioactive. As plutonium-240 concentrations increase, handling and processing the plutonium becomes more and more hazardous. Therefore, it is highly unlikely that a foreign power would attempt extracting plutonium from the spent fuel rods from a civilian power reactor unless the objective is a very low yield for terrorism.